one of the things that we can do is like using the same previous linear equation that we are interested in solving, we can use this idea to solve for this class of problems. So here, what is the transformation matrix? And this, the transformation matrix is this. Okay. Now, if you look into the unknown vector, right, which is the parallelogram constructed by unknown vector and I, that is here, and if we apply the transformation, this parallelogram is going to get transformed, right, and this parallelogram is going to get changed, and the area of that is going to also change, right. So after applying this transformation, you can see previously this was the original parallelogram. Now this parallelogram area has, in this case, extended, and we land here, right. So what we can do is we can use the area before the transformation, which is this, and the area which is after the transformation, which is essentially captured by the determinant of this, two different matrices, and use that to find out the unknown vector. So let's see how we can do that, right? So after we apply the transformation, we know the determinant is factor how much things are changing after the transformation, right? So area after transformation is going to be equal to the determinant of M, which is the transformation matrix, multiplied by the previous area. Okay. So what is the previous area that we have? If you look into this figure, the previous area was this. Okay. And what is the area after transformation? This is the area that we have of overall the transformation. So if you take this previous area and multiply that by the determinant of this transformation matrix, that should be equal to the parallelogram area that you see here, and that's the geometric interpretation, and that's the way to think about geometrically how we can use the Cramer's rule to solve for a set of equations that we have. Okay, so again, this area is scaled by this determinant of the matrix, right? So we can say that after transformation, the parallelogram defined by the first vector transformed I and output vector V, that is out there. So, okay, so again, now we can use this idea that I area after transformation is equal to factor times previous area, but that factor F is essentially determined by the determinant of the transformation matrix M that we have. Okay, so again, determinant, what is the previous area? As we have already shown in a couple of slides before, that this previous area will be equal to Y, right? So from there, what we can do is we can solve for Y by doing this, where Y is equal to area after transformation divided by determinant of the matrix M. Okay. Now, area after transformation is obtained by taking the determinant between the vector transformed I and the output vector V. Okay, so what we need to do is we need to find out an equation that describes this, and this is the intuitive meaning of what we can do. We can find out what is the area after transformation by taking the determinant between the vector of the transformed I and output vector V. So what is that? So output vector, transformed I was 0, 2, and what was the vector V? Known vector, which was on the right hand side of the equation, that was -4, 2. So if I take a determinant of that and then divide by the determinant of M, that helps me in solving the Y. And this is exactly how the equations or the the intuitions and the other could be scaled to higher dimensions. For example, if you have 3 variable and 3 equation, then rather than having parallelogram, you will have parallelepiped volume, and you can use the area, not the amount and extension of shrinking of the volume in the 3 dimension, and that will help you in basically coming up with the equations that will help you in solving 3 variables, 3 equations. So here is one that we can see geometrically how we can understand what the transformation does and use that, the area based before and after transformation, and then area before and after is related by the determinant of the matrix M. We can use that to basically define the set of equation that is used to solving linear equations. So here this approach gives me solutions for Y, and similarly I can now simplify this and solve for this. So in this case, the Y is going to be essentially equal to 2. Now similarly, we can use same intuition and same geometric ideas to solve for x2. So let's carry that out, right? So the parallelogram defined by the first basis vector transformed J and the output vector is essentially can be used to solve for x. So here is the parallelogram that it gets transformed j and the output vector. So this is something there, and we had initially a transformed, before transformation the parallelogram was here, but after transformation the area has extended. So we can now use this idea, which is x is area after transformation divided by the determinant of m. And if that's the case, we can find out the area after transformation by taking the determinant between the vector transform j and output vector. So if you take this figure, this two vector, if you compose them and create a matrix and take the determinant of that matrix, that will be the area after transformation, right? And divide that by the determinant of m, that will help you in essentially solving for x, okay? So again, if that's the case, we can write this x as, determinant of -4, 2, -2, 2, 1 divided by the determinant of the transformation matrix, which is 0, 2, -2, -1. And from there, we can simplify this and we can solve for this. And again, x will also come out to be 2. So in this case, x and y both are equal to 2. And this is how, geometrically you can understand what is going on with the Cramer's rules, and the equations that come into pictures that you see in the numerical implementation has this geometrical meaning, and hopefully you understood what is happening when geometric transformations are happening from unknown vector to a known vector. We can use these ideas of determinant to solve for those unknown vector values.